Today we're going to talk about inelastic neutron scattering. And this is going to contrast the very simple description that we had in the first couple of lectures, in which we described potential scattering of neutrons. In that description, the sample that was scattering actually had no dynamics at all. It was just this magic static potential from which the neutrons were going to scatter, and they could not exchange energy with the sample. We're now going to make a more detailed description which will include the possibility of changing the state of the sample during the scattering process. I'm going to start off by talking about the kinematics of scattering, and then I'm going to continue to develop an expression for the partial differential inelastic scattering cross-section. So first, a few words about the kinematics. The experiment is in principle quite simple. I start off with an incident plane wave neutron state, and then I'm going to interact with the sample, scatter into a state k prime. In this scattering process, from general principles, momentum as well as energy must be conserved. And so I would expect that if I change the momentum of the neutron, as I clearly do in this case, then I would also have changed the momentum of the sample and have some momentum imparted to the sample during that scattering process. Let me write the equations for conservation of momentum and energy. First, conservation of momentum. Clearly, the incident momentum, let's say the momentum prior to the scattering, is in units of h bar k, and that has to match the momentum of the scattered neutron, which we denote as k prime, plus the momentum which is delivered to the sample, which we're going to denote by capital Q. And so, developing this expression, if we imagine being able to control k and being able to measure k prime, then we can infer that a certain amount of momentum q equals to k minus k prime has been transferred to the sample. All right, so that was conservation of momentum, and those then represent essentially three equations, one for each of the Cartesian components of momentum transfer. But we have an additional equation which comes from the demand that we also conserve energy in the scattering process. And let's see what those equations look like. Energy conservation says that the energy prior to scattering, which we're going to denote E, that's simply the kinetic energy of the neutron prior to scattering, that has to be equals to the energy carried away in kinetic energy by the scattered neutron plus an amount of energy that may be delivered to the sample. I'm going to denote that by h bar omega. So again, rearranging this expression, we find that energy transferred to the sample is equals to E incident energy minus scattered energy. And so an inelastic neutron scattering experiment will be able to measure what we would call a dispersion relation for collective excitation in the material by matching the energy transfer, or by matching the energy and momentum of that collective excitation. So these expressions, simple as they are, hold a lot of information about the nature of the inelastic scattering process, and you can already begin, I think, to see here how the inelastic scattering experiment will be able to reveal important information about the collected properties of materials. Now, I want to develop these simple concepts a little further by looking at the all-important scattering triangle. And so let me first remind you what it looks like in the case of elastic scattering, something we did a couple of weeks ago. In the elastic scattering case, the scattering triangle is an equilateral scattering triangle. This would be incident wave vector, and let's say that the scattered wave vector looks like that. I draw them tip to tip. I have the freedom to do that, so I can translate my vectors any which way I would like. So draw them tip to tip. Momentum transfer then looks like that, Q. And if I denote the angle between incident and scattered neutron by 2 theta, then looking at this triangle, we can readily show that the length of this vector Q is equals to twice the length of the wave vector of the incident and scattered neutron, they have the same length, times sine of theta, which is actually half of the scattering angle. So this is just a simple geometry of the elastic equilateral scattering triangle, and this expression essentially turns into what you're familiar with as Bragg's law when we have a periodic solid. Because in a periodic solid, we have the condition that Q must be equals to a reciprocal lattice vector, which we call tau, and this also requires that the length of these vectors must match each other, and so we end up with an expression, a condition to have Bragg diffraction, which is that reciprocal lattice vector length must match 2k times sine theta. That's essentially Bragg's law. It is a necessary condition to have Bragg diffraction, not sufficient because Bragg's law itself is actually a vector identity between momentum transfer to the sample and a reciprocal lattice vector. So that was sort of the little discussion we could have regarding the equilateral elastic scattering triangle. Now in the case of inelastic scattering, we can draw a similar scattering triangle, but it's now no longer an equilateral scattering triangle. We would have incident wave vector, draw it here. And again, I'm going to draw the wave vectors tip to tip. This might be k prime. And momentum transfer then lays as such. The angle we are still going to denote it as 2 theta. So this is my typical inelastic sort of general scattering triangle. Then you may ask, can I relate the length of Q to the directions and lengths of k and k prime? And of course, that is possible using the cosine relation. We can readily write down that Q squared is equals to k squared plus k prime squared minus 2k k prime cosine 2 theta. So this expression, in a sense, replaces the simple expression we had in the elastic case. And now there's an interesting observation that we can make regarding the range of wave vector transfer that can be accessed in an elastic as opposed to an inelastic scattering experiment. So first, in the case of elastic scattering, you can readily see from this expression that Q must be always less than twice the length of the incident neutron wave vector, and it has to also be greater than 0. It can get all the way down to 0. That occurs when the two legs of the equilateral scattering triangle join each other and wave vector transfer just vanishes. Now in the case of inelastic scattering, k prime has become smaller than k typically, or it could be longer than k. Either of those two are possible, but it's not going to have the same length because it is an inelastic process. As a result of that, I'm never going to actually be able to let Q become 0. If you imagine swinging this wave vector around like that, then there's no direction you can have it point in and actually manage to make Q go away entirely. In fact, the smallest value of Q that you can obtain is going to be absolute value of k minus k prime. And this is going to happen when 2 theta is equals to 0. So the smallest wave vector transfer occurs in what we might call the forward scattering direction, and that smallest wave vector transfer has a length of k minus k prime absolute value. So that's a lower bound on Q, and the upper bound is going to occur when I'm in the backscattering condition. So when k and k prime are completely opposed to each other, then the length of Q is going to be equals to k plus k prime. So that's the range of momentum transfer that I can access for an inelastic scattering experiment when k has a different length than k prime. Now let's consider the case of transferring almost all the energy of the incident neutron to the sample. So this would correspond to a scattering triangle which looks something like this, where k is like that, but then k prime is very, very short, maybe even completely absent. Then, as you can see, Q in its length becomes essentially equals to k. So in a very strongly elastic process in which h bar omega would be approximately equals to EI, or approximately equals to energy of the incident neutron, then not only do I transfer all of the energy to the sample, but necessarily I also transfer all of the incident momentum to the sample. So I can say when h bar omega is approximately equals to E, then Q is approximately equals to K. So that's a process in which I actually managed to bring the neutron to a halt in its scattering from the sample. And it turns out that that's actually a quite a useful type of situation which is used to create so-called ultra-cold neutrons. You bring the neutrons to a halt through their interactions, through their inelastic scattering from a material, and it's used to create high densities of ultra-cold neutrons in measurements of the neutron lifetime. All right, so that's about how much we can extract by thinking about the simple kinematics of the scattering process. And now to actually connect in a more quantitative fashion to the dynamic processes in the material, we have to begin to look at the expressions for the corresponding scattering cross-sections. And I'm going to pick up essentially where we were when we talked about the elastic scattering experiments, and I'll somewhat modify the expressions so that they become usable also in the case of inelastic scattering. So let me first remind you what we derived in the case of elastic scattering. So there we wrote down expressions for the differential scattering cross-section, d sigma d omega, which essentially counts the number of neutrons that arrive in a certain direction that we have established by the location of the detector in units of the number of neutrons which have arrived at and have interacted with the sample. So this expression took the following form. I'm just going to write the results, and you have seen it before. It was a dot product of the neutron current density near the detector with the area element representing the detector. And then I had to divide by the current density incident on the sample and by the solid angle subtended by the receiving detector. That's my expression for the differential scattering cross-section, and we could then develop expressions for these current densities based on the real space representation of this scattering state of the neutron. And the expression looked as such. There was an overall neutron density multiplied by a velocity, which was going to be h bar k prime divided by m, and now keeping track of the potentially different lengths of the incident and scattered wave vector. And then I'm also going to, let's see what's missing. Yeah, here I have my modulus squared scattering amplitude divided by r squared. You may remember that this expression arose as a prefactor to the spherical wave emanating from the sample. And then I still have my area of the detector showing up. So that's the numerator, and the denominator would have neutron density, and it would have a velocity of the incident neutron, so density times the velocity is the current density, and then again multiplied by my solid angle. So those expressions you've seen, I think that was in the second lecture. And in those expressions, many things cancel. The density cancels, all these fundamental constants cancel. D omega cancels with dA over r squared, which is the solid angle, and this guy stays around, as does this ratio of k prime over k. So I get k prime over k times absolute value of f of theta squared by scattering amplitude squared. And we can actually work from this expression as we develop the expression for inelastic scattering. Now, the ratio k prime to k actually vanishes in the case of elastic scattering, but I'm going to leave it here because I want to gradually morph this expression into one that's appropriate for dealing with inelastic scattering. And in that case, k prime and k will actually be different from each other. And doing that allows you to basically appreciate that this ratio of k prime over k that enters into the scattering cross-section actually arises from the ratio of velocities of the scattered neutron to the incident neutron. But now let me look a little bit at this expression for f of theta, and we'll gradually let it graduate into one that can be used to describe inelastic scattering. And for that, I'm going to move to this side of the board. So I'm going to come all the way back over here. So the scattering amplitude. Let me write the expression that we obtained. That was 4 pi squared over m h bar squared. And then there was a matrix element, k prime, and there was a t matrix, t operator, k vector. Right. Expression. Okay, so now the first thing we're going to do is we're going to be working within the Born approximation, which means that we're going to replace the t operator with the interaction potential. That's my first step. Nothing very surprising with that. Secondly, we now have to take into account that the sample may actually be changing its state during the scattering process. So it may be going from a state which I'll denote by lambda. So let's say initial state of the sample will be labeled by lambda. This label, if you will, may contain all of the quantum numbers that describe that particular state, or may contain whatever is needed to describe that particular thermodynamic equilibrium. And then we have the final state, which I'll denote by lambda prime. Now, in my initial discussions here, these are going to be specific quantum states. I'm going to write the scattering amplitude associated with the transition between a specific quantum state lambda and a specific secondary state lambda prime. And so those I'm going to have to carry along with my wave vector index for the neutron, both in the final state as well as the initial state. So this is the initial state of the combined neutron sample system, lambda and k, and this is the final state of the combined sample neutron system. And the idea is that this operator is now having effect both on the sample and on the neutron. Okay, so now I can add that into my expression for the scattering cross section, and I'm going to now write our first example of a partial differential scattering cross section. And let me just contrast that with our expression for d sigma d omega that I previously developed over there. The expression for d sigma d omega talks about the amount of neutrons received in a detector, which is specifying a certain direction of scattering. However, I'm not keeping track of the energy of the scattered neutron at all in that case. But now, since I'm going to be doing spectroscopy, and I'm going to be interested in inelastic scattering events, I'm actually going to be discriminating not only in the direction of the neutron, but also the energy of the scattered neutron. And so let me then write down the expression for the partial differential scattering cross-section. You can see that a dE prime appeared in the denominator because I'm looking at scattering into a specific energy of scattered neutron. And as I said, I'm going to develop it from the expression for the elastic differential scattering cross-section. So this should be equal simply a k prime of a k times absolute squared of this scattering amplitude. And you can see that I've made this one graduate into the form which is appropriate for inelastic scattering. So let's pop that one in. Minus 4 pi squared m over h bar squared, because I'm going to have the squared scattering amplitude. And then comes lambda prime k prime interaction potential, lambda k. And this thing has to be squared. But there's one thing more missing, which we can appreciate when we notice that the denominator has energy in it. So we need, in this expression, which so far has dimensions of an area, we need something with dimensions of 1 over energy. And that is going to be the term which will enforce energy conservation. As we mentioned previously, the energy delivered to the sample must result in an increase in the energy of the sample. And so there must be a difference in energy of the initial and final state of the sample, which has to match the difference in energy between the initial and final state of the neutron. So specifically, energy transferred to the sample, which we previously denoted as h bar omega, should be equals to or must be equals to the difference, final energy of the sample minus initial energy of the sample, E lambda. These things must match each other because I cannot have lost energy in the overall process of having the neutron interact with the sample. And to enforce this condition, I'm going to place a Dirac delta function h bar omega minus E lambda prime minus E lambda as such. So here I have an expression for the partial differential scattering cross-section involving a transition of the sample from state lambda to state lambda prime. Now, while I would like to be able to measure something like that, that's in general not going to be possible because I can't separately control, in general, the initial state of the sample and the final state of the sample. So I'm going to have to consider a situation where the initial state is established through the device of thermodynamic equilibrium. So I'm going to put the sample into some sort of thermodynamic equilibrium. And then I'm going to have to consider all possible final states of the sample. I have no way of controlling what the final state of the sample will be through this scattering event. And so this cross-section is one that I cannot really measure. What I'm instead going to do, and I'm now going to transfer over here, what I'm instead going to do is I'm going to think about an initial thermodynamic equilibrium state and a combination of all possible final energy states. For the initial state, I'm going to sum over all possible states of the sample, so all the quantum descriptions, or all possible initial states of the sample, and then some sort of probability of occupying that particular state. And of course, under general conditions, I would expect P lambda to be equals to e to the minus beta, E lambda divided by the partition function. But in fact, I'm not going to carry this expression around very much. That's basic thermodynamics that we don't need at this particular point. So that'll be an initial state, and then I'm going to sum over all final states. And that means that my partial differential scattering cross-section now is going to look as follows. Much of it remains the same. I have a k prime of the k. I have my numerical factor squared. And then I have a summation over all initial and final states of the sample, my weighting probability distribution, because I'm measuring this partial differential cross-section in a thermodynamic equilibrium. And then I need my other terms, which is my matrix element, lambda k, v, lambda, sorry, that was prime, and then lambda k mod squared. And I have my Dirac delta function for energy conservation. So that's a wonderful expression, and that really is now has all of the detail in it that we're going to need in our description of inelastic scattering in the Born approximation. And I want to now basically continue bringing forward this expression into forms that are useful for describing various types of inelastic scattering. And more specifically, we're going to be looking at inelastic nuclear scattering and inelastic magnetic scattering. And I'm going to try to keep the duration, if you will, in parallel, and then when required, I will eventually introduce the particular interaction potential that pertains to those two cases. I'm also going to try to keep the expressions as general as possible until the point where maintaining this generality would induce too great complexity. So when there is such complexity required for you to understand your experiments, then you'll have to go and consult the various books. And in particular, the one that I'm going to recommend and which I'm using in what I'm writing down today is Stephen Lovesey's book on theory of thermal neutron scattering from condensed matter. This book is listed, I believe, also on the course webpage. So still keeping the option of both nuclear scattering and magnetic scattering open, I'm going to consider now what is going to be the form of this potential. And the situation that I'm going to be dealing with here is one typically of a crystalline lattice in which I have copies of potential in many, many different unit cells. So most of the situations we'll deal with are actually periodic lattices, but actually in my initial expressions, I don't really need to impose the requirement of a periodic lattice. All I need to do is to consider the case where the potential, the overall potential, V of R, the interaction potential, is actually a sum over a number of sites which have identical interaction potentials labeled by L, and depending on now R minus RL. So this R minus RL ensures that I place the same interaction potential, which might be sort of a unit cell interaction potential. I place it on all different sites, which are called out by these set of vectors that are denoted RL. So at some point, these will become the vectors of a Brevet lattice, but at this point, it actually isn't required to be so just yet. But let me see what happens when I introduce this guy into my partial differential scattering cross-section. And I'm going to do that on this board over here. Good, so basically, I'm going to be operating essentially just on this part of the expression. And what's going to happen there is that I'm going to change these wave vector components into plane wave states, and then I'm going to carry out a position integral, which will essentially extract the neutron part of the matrix element, leaving untouched the state of the sample. And so let me show you how that comes out. There's again, most of it hasn't actually changed. I'm still writing it down. This term 4 pi squared here actually is going to be relegated to the denominator because of the way these plane wave states are normalized. Those carry around a 1 over 2 pi to the minus 3 half power. And this will then move this 4 pi squared to the denominator. So I end up getting a m over 2 pi h bar squared. And I still have my summation over incident and final states, my thermodynamic weighting factor. And then in my potential, I'm now going to get in my potential, I still have my absolute value squared, but now I have actually a sum of all these different lattice positions of an e to the I q dot e to the I q dot RL, and then I will have my matrix element, which is a lambda prime, and then a VL of Q vector, and then lambda, and all of that has to be squared. And then finally, I have my Dirac delta function, lambda prime minus E lambda. Okay, so what showed up here was actually a Fourier transform of the interaction potential in cell VL. Let me write out exactly what that one looks like. VL of Q is equals to integral d3 of R e to the I Q dot R, and then VL of R. So that's as far as we've taken it so far, and that'll complete our lecture.